Data modeling is a blend of algorithm selection, hyperparameter tuning, feature engineering, and thorough evaluation. It's the art and science of making data tell a story. We commence with a baseline model to set our benchmark. This is followed by time series forecasting using Arima and an exploration into the emotional undertones of data with sentiment analysis. The selection of pivotal features is optimized using XGBoost. Venturing deeper, we employ deep neural networks. Here, we navigate through sequence prediction using LSTM networks, leverage spatial data with convolutional networks, integrate diverse stock data, and enhance our predictions using Bayesian optimization. Rounding off, we manually undertake pattern recognition, highlighting the significance of human touch in automated processes. Lastly, we embrace Q-learning, a reinforcement technique, teaching our model through a system of rewards and penalties. Code imports necessary modules such as OS, Pandas, Matplotlib, Seaborn, Warnings, NumPy, Array, Reload, Gaussian NB, and XGB classifier. It also sets the figure DPI for plots. The purpose and functionality of the code are not provided, as it might be related to a specific project or analysis. This Python code imports various modules from the stats models and sklearn libraries, which are commonly used in time series analysis and modeling. The first set of imports are related to Arima and Sarima modeling, which are techniques for modeling and forecasting time series data. The next set of imports are related to visualizing autocorrelation and partial autocorrelation plots, which are used to determine the order of the autoregressive and moving average components of the Arima model. Finally, the code imports functions for computing performance metrics such as mean squared error, confusion matrix, F1 score, and accuracy score, which are commonly used to evaluate the performance of time series models. Code imports several modules and classes from the TensorFlow library to build and optimize neural network models using Keras. The imported modules include TensorFlow.Keras, the Keras API for TensorFlow 2.0, TensorFlow.Python.Keras.optimizer_v2.rmsprop, the rmsprop optimizer from TensorFlow, functools.partial, a function to create partial functions with specific arguments, TensorFlow.Keras.optimizers, the module that contains various optimization algorithms. TensorFlow.Keras.models, sequential and TensorFlow.Keras.models, model, the classes to create sequential and functional models respectively, TensorFlow.Keras.layers, a module that provides different types of layers for building neural networks, TensorFlow.Keras.utils.plot_model, a utility function to visualize the models. Additionally, the code also imports the Bayesian optimization class from a library called Bayesian optimization for hyperparameter tuning. The code does not provide any specific functionality or implement any specific algorithm, it simply prepares the necessary tools and modules to work with TensorFlow and Keras for building and optimizing neural network models. One code imports a module called functions and another module called plotting. The functions module likely contains custom-defined functions that can be used in the code. The plotting module likely contains methods and functions that allow for creating plots and visualizations. If code sets the random seed for the number py random number generator to a specific value, in this case, 66. Setting the random seed ensures that the same sequence of random numbers is generated each time the code is run, allowing for reproducibility of results. Reading stocks data and keeping it in dictionary stocks. Date feature becomes index. Reads all files in the data/stocks directory, and for each file, if the file is a CSV file, it reads the file using pandas read_CSV function and assigns the resulting data frame to a dictionary called stocks, with the file name, without the .csv extension, as the key. It also sets the date column as the index of the data frame by using the index_call parameter. Finally, it converts the index to a datetime format using PD to _datetime. Baseline model. Baseline model would serve as a benchmark for comparing to more complex models. Python code defines a function called baseline_model, which takes in a series or array of stock data. The function generates random numbers between 0 and 1, and compares them with the true values of the stock data. It then calculates the accuracy score by comparing the true values with the randomly generated numbers. The function returns the accuracy score. Accuracy. Python code computes the accuracy of a baseline model for predicting the returns of the TSLA stock. The baseline model is assigned to the variable baseline_model. The model's accuracy is calculated by passing the return column of the TSLA stock data to the baseline_model function. Finally, the calculated accuracy is printed in percentage format. Distribution. Code does the following. 1. It creates an empty list called base_preds. 2. It uses a for loop to iterate through the range from 0 to 999, 1000 iterations. 3. Inside the loop, it appends the result of calling the baseline_model function on the return column of the stocks, TSLA, data frame to the base_preds list. 4. After the loop, it imports the pyplot module from the matplotlib library, sets up the figure size and style. 5. It plots a histogram with 50 bins using the data from base_preds. The histogram is colored with hashtag 4AC2FB. 6. It sets the title of the plot to baseline model accuracy with a font size of 15. 7. It adds a vertical line at the mean value of base_preds on the plot, colored black with a dashed line style and a line width of 2. 8. Finally, it displays the plot. Conclusion. The model on average has 50% accuracy. We take this number as a guideline for our more complex models. Autoregressive integrated moving average, Arima, is a model that captures a suite of different standard temporal structures in time series data. Model parameters. The parameter P refers to the number of lag observations incorporated into the model. This is often termed as the lag order. It's essential for determining the dependency on previous time steps. Next, D represents the number of times raw observations undergo differencing. This process is crucial for making certain time series stationary and is commonly referred to as the degree of differencing. Lastly, the parameter Q denotes the size of the moving average window. This is a critical component in smoothing the data over a specified interval, and it's typically known as the order of moving average. Train and test data to evaluate performance of Arima model. Python code first prints a statement that displays the number of entries in the Tesla historical data. It uses the dot format method to insert the value of stocks, TSLF, dot shape, 0, into the string. After that, it selects the return column from the Tesla historical data using the stocks, TSLF, return notation, and then it displays the first few rows of that column using the dot head method. Let's take a look at the autocorrelation function below. The graph shows how time series data points correlate between each other. We should ignore first value in the graph that shows perfect correlation, value equals 1, because it tells how data point is correlated to itself. What's important in this graph is how first data point is correlated to second, third, and so on. We can see that it's so weak, it's close to 0. What does it mean to our analysis? It means that Arima is pretty much useless here, because it uses previous data points to predict following. Python code sets the figure size of the plot to be generated as 16 inches in width and 3 inches in height. Then, it plots the autocorrelation function ACF of the return column of the TSLA data frame from the stocks dataset. The lags parameter is set to range from 0 to 299. Finally, it displays the plot. In conclusion, we're going to try different orders and see how well they perform on a given data. Is performing Arima, autoregressive integrated moving average, forecasting on a time series data. Here's a breakdown of what the code does. It defines a list of different Arima orders, combinations of P, D, and Q values, that will be used for the forecasting. It splits the time series data into train and test sets. It initializes an empty dictionary called all_predictions to store the predictions for each order. It iterates over each order in the list of orders. Inside the loop, it sets up a try-except block for error handling. This is because some combinations of orders may not work for the given data. It initializes a list called history with the values from the trained set. It then iterates over the test set and performs the following steps. it creates an Arima model with the specified order. It fits the model to the history data. It forecasts the next value in the time series. It appends the predicted value to the order_predictions list. It adds the actual value from the test set to the history, effectively updating the model for the next iteration. It prints the progress of the prediction. After iterating over all the orders, it calculates the accuracy of the predictions by comparing the binary representation of the test set with the binary representation of the predictions. It prints the order and the accuracy. It adds the order_predictions to the all_predictions dictionary. If there is an exception, typically due to incorrect order, it prints an error message and continues to the next order. Overall, this code performs Arima forecasting on the given time series data using different orders and stores the predictions for each order in a dictionary. It also calculates the accuracy of the predictions for evaluation. View predictions. Python code creates a figure with multiple plots. The first plot is named Big Plot and consists of a line plot with two lines, one representing the test data and the other representing predictions. There is a legend displaying the labels for each line, and a title, x-axis label, and y-axis label. There is an arrow annotation pointing from the coordinates 15, 0.05 to 150, 0.2 within the plot. A rectangle patch is also added to the plot, positioned at 0, -0.05, with a width of 30 and height of 0.1. The rectangle has a dashed line style, yellow face color, black edge color, and a transparency of 0.5. The second plot is smaller and positioned at 0.25, 1, with a width of 0.2 and height of 0.5. It displays a line plot of the first 30 elements of the test and predictions data. The x-axis and y-axis labels are hidden. Finally, the plots are shown. This Python code creates a histogram plot comparing the distribution of true values and predicted values for a stock, TSLA, within a specified range, from index 1900 to 2300. The true values are plotted with a blue color and labeled as true, while the predicted values are plotted with a pink color and labeled as predicted. The code also adds a vertical line at the x-coordinate of 0 in a black color dashed line style. The title of the plot is set as Arima True versus Predicted Values Distribution. Finally, a legend is added to the plot to identify the two distributions and the plot is displayed. Interpreting results. This Python code performs the following tasks. 1. It converts a subset of the TSLA column from the stocks data frame, specifically the rows between index 1900 and 2300, into a binary format using the binary function from the functions module. This binary conversion is stored in the variable test_binary. 2. It converts a subset of all_predictions using the indices 0, 1, 0 into a binary format using the binary function from the functions module. This binary conversion is stored in the variable train_binary. 3. It calculates the true negatives, Tn, false positives, Fp, false negatives, Fn, and true positives, Tp, by applying the confusion_matrix function from the sklearn.metrics module to the test_binary and train_binary variables. 4. It calculates the accuracy of the binary predictions by using the accuracy_score function from the sklearn.metrics module, which takes the test_binary and train_binary variables as input. 5. It prints the sum of true positives and true negatives, the sum of false positives and false negatives, and the accuracy percentage. The true positive and negative values are substituted into the first print statement using the format method, while the false positive and negative values are substituted into the second print statement. The accuracy is formatted to display one decimal place. Sentiment analysis. To use news sentiment to predict returns next day. Code imports a CSV file named Tesla_headlines.csv into a pandas data frame called Tesla_headlines. The index_call parameter is set to date, which means that the date column will be used as the index for the data frame. Python code combines the TSLA column of the stocks data frame with the mean sentiment value from the sentiment column of the Tesla_headlines data frame after grouping by the date column. This Python code fills missing values in the variable Tesla with the value 0, modifying the original variable. It uses the matplotlib library to create a line plot. It sets the style of the plot to a white grid style, and sets the size of the figure to be 16 inches by 6 inches. It then plots two lines on the figure, one representing the sentiment of Tesla news from January 10, 2019 to September 5, 2019, and the other representing the daily returns of Tesla stock during the same time period. The plot includes a legend, a title, and is displayed using the show function. This Python code calculates the correlation between the sentiment column and the return column of a data frame. The data used for calculations is obtained from the Tesla data frame for a specific date range, from January 10, 2019 to September 5, 2019. The sentiment column is shifted by 1 day using the shift function before calculating the correlation. Between news and price movement is negative. Prices moves in the opposite direction, which is wrong. Positive news supposed to drive prices up, not the opposite way. Feature selection with XGBoost. XGBoost will be used here to extract important features that will be used for neural networks. This might help to improve model accuracy and boost training. Training will be performed on scaled Tesla dataset. Code applies a scaling function to the TSLA column of a variable called stocks. The scaling function scales the values in the column to fit within the range of 0 and 1. The resulting scaled values are stored in a variable called scaled_TSLA. Python code assigns the variable x to a subset of the variable scaled_TSLA, excluding the last element. Then, the variable y is assigned to the shifted values of the TSLA column in the stocks data frame. The shift -1 function shifts the values one position forward, and the :1 indexing is used to exclude the last element from the series. This Python code initializes an XGB classifier model and fits it using the training data, x and y, starting from the 1500th index. This Python code calculates the feature importance of a machine learning model, XGBoost, and plots a horizontal bar graph to visualize the results. The important_features data frame is created with two columns, feature, which contains the names of the features, and importance, which contains the corresponding importance values calculated by the XGBoost model. The data frame is then sorted in ascending order based on the importance values. The code then creates a plot using matplotlib, specifying the size of the figure, 16 by 8, and the style of the grid. The horizontal bar graph is created using the bar function, with the features as the y-axis and their corresponding importance values as the bar lengths. The bars are colored using the hexadecimal color code #4AC2FB. The title of the plot is set as XBoost, feature importance, Tesla, and the x-axis label is set as importance. Finally, the plot is displayed using the show function. 5. Deep neural networks. This Python code performs the following steps. 1. Sets the value of a variable n_steps to 21. 2. Scales the TSLA column of the stocks data frame using the scale function from the functions module, and assigns the scaled values to a variable scaled_TSLA. 3. Splits the scaled_TSLA values and the lagged values of the return column of the TSLA stock into training and testing datasets using the split_sequences function from the functions module. The training dataset is assigned to variables x_train and y_train, while the testing dataset is assigned to variables x_test and y_test. The split is performed using a sliding window approach with a window size of n_steps. The split ratio is set to 80% training and 20% testing. 5.1 LSTM network. This Python code is creating a deep learning model using the keras library in Python. The code begins by calling keras.backend.clear_session, which clears any existing model from memory. Next, the code calculates the number of time steps, n_steps, and number of features, n_features, in the training data, x_train. Then, a sequential model is created. This is a linear stack of layers. The model architecture is as follows. 1. The first layer is an LSTM layer with 100 units, which has a rectified linear unit, ReLU, activation function and returns sequences of outputs. 2. The second layer is another LSTM layer with 50 units, which also uses ReLU activation function but does not return sequences. 3. The third layer is a dense layer with 10 units. 4. The fourth layer is another dense layer with 1 unit. After defining the model architecture, the code compiles the model using the atom optimizer, mean squared error MSE, as the loss function, and mean absolute error MAE, as the evaluation metric. The line model.summary is typically used in a Python program that utilizes a deep learning library such as Keras or TensorFlow. It displays a summary of the model which includes the layers, shape of input-output tensors, and number of parameters in each layer. This helps in understanding the architecture and structure of the neural network model. Code trains a model using the fit function in TensorFlow's Keras API. It trains the model on the training data, x_train and y_train, for 100 epochs. The verbose parameter is set to 0, which means that no output will be printed during training. The validation_data parameter is set to x_test, y_test, which means that the model's performance will be evaluated on the test data after each epoch. After training is complete, the code uses the plot function from the matplotlib.pyplot library to create a figure with 2 line plots. One plot represents the loss of the model during training, model.history.history, loss, and the other plot represents the validation loss, model.history.history, val_loss. The legend function is used to add a legend to the plot, and the title function sets the title of the figure. Finally, the show function is called to display the figure. It evaluates the performance of a machine learning model using a set of test data. It calls the function evaluation from the functions module, passing in the test data, x_test and y_test, the model, and some optional parameters. The function returns the predicted values, pred, the true values, y_true, and the predicted values with the specified number of predictions, y_pred. Additionally, it shows a graph of the evaluation if show_graph parameter is set to true. The network wasn't able to pick up the underlying patterns. Prediction is roughly 50%, which is same as random guess. 2. Convolutional network is a Python script using the Keras library to define and compile a convolutional neural network (CNN) model. The first line, keras.backend.clear_session, is used to clear any existing models or layers in the current session. The n_steps and n_features variables are then initialized with the shape of the input data x_train. These variables represent the number of time steps, rows, and features, columns, in the training dataset. The model object is created as a sequential model, which means that layers are added one after another. The model is then defined with the following layers: CONV1D layer with 20 filters, output channels, kernel size of 2, and ReLU activation function. The input_shape parameter specifies the shape of the input data. Max pooling 1D layer with pool size of 2, which reduces the dimensions of the input by taking the maximum value in every 2 consecutive elements. Flatten layer, which converts the pooled feature map into a vector to be passed to the next layer. Dense layer with 5 units and ReLU activation function. Dense layer with 1 unit, which represents the output layer of the model. After defining the layers, the model is compiled with the following settings: optimizer set to atom, which is a popular algorithm for stochastic optimization. Loss set to MSE, which stands for mean squared error, a common loss function for regression problems. Metric set to MSE, which means that the mean squared error will be used as an additional metric to measure the model's performance during training. Given code is calling the summary method on a Python object called model. This method typically belongs to machine learning frameworks such as Keras or TensorFlow and is used to print a summary of the neural network model architecture. The summary includes details like the number of layers, shapes of the layer outputs, and the number of trainable parameters in the model. Code trains a model using the fit function. It takes the training data x_train and y_train, and trains the model for 25 epochs. The verbose parameter is set to 0, so no output will be displayed during training. The validation underscore data parameter specifies the test data x underscore test and y underscore test for validation during training. The use underscore multiprocessing parameter is set to true, indicating that multiprocessing should be used for faster training. After training, the code plots the training loss, model.history.history, loss, and the validation loss, model.history.history, val underscore loss, using plt.plot. The plt.figure function is called to specify the size of the figure. The legend is added using plt.legend and the title of the plot is set to con training process with plt.title. Finally, plt.show displays the plot. Code evaluates the performance of a machine learning model by comparing its predictions, stored in y_pred, with the true labels, stored in y_true. The evaluation is performed using a set of test data, x_test, y_test, and various evaluation metrics are calculated. Additionally, the code generates a graph showing the predicted values alongside the true labels. The evaluation is conducted using the evaluation function from the functions module, with options for generating random predictions, specifying the number of predictions, and displaying the graph. The results of the evaluation are stored in the pred variable. Able to pick up the underlying patterns. Prediction is roughly 50%, which is same as random guess. 5.3 combines stocks data. Training on 18 different stocks. Code is concatenating a list of data frames called stocks into a single data frame called all_stocks. The resulting data frame will have all the rows from each data frame in the list, and the index will be reset to a new consecutive index. The ignore_index equals true parameter ensures that the concatenated data frame will have a new sequential index starting from 0. This Python code performs the following tasks. 1. It scales the data stored in the all_stocks variable using the scale function from the functions module. The scaled data is then assigned to the scaled_all variable. 2. It sets the value of n_steps to 21. 3. It calls that split_sequences function from the functions module to split the data into training and testing sequences. The input for the function includes the scaled data stored in scaled_all, the lagged values of the return column from the all_stocks dataset, the number of steps n_steps, a split parameter set to true for splitting the data, and a ratio parameter set to 0.8 for an 80-20 training testing split. The resulting training and testing sequences are assigned to the variables x_train, y_train, x_test, and y_test, respectively. Sets up a neural network model using the Keras library in Python. The code first clears the Keras session to reset any existing models. Then it defines the number of steps and features in the training data. The model is then created and configured with several layers. The first layer is a 1D convolutional layer with 500 filters, a kernel size of 10, and a rectified linear unit, ReLU, activation function. It takes input with the shape of n_steps, n_features. The second layer is a 1D max pooling layer with a pool size of 10. The third layer is a flattened layer that reshapes the previous layer's output to a one-dimensional array. The fourth layer is a fully connected, dense, layer with 500 units and a ReLU activation function. The fifth layer is another fully connected layer with 100 units and a ReLU activation function. The last layer is a single unit with a sigmoid activation function, used for binary classification. Finally, the model is compiled with an optimizer, Atom, and a loss function, mean squared error, MSE. This Python code trains a model using the fit method on the specified training data, x_train and y_train, for 25 epochs. It then plots the loss and validation loss of the model using the plt.plot function and the model.history.history dictionary. The loss and val_loss values are retrieved from the dictionary and are plotted against each other. Finally, the legend is added to differentiate between the two lines and the plot is displayed using plt.show. This Python code evaluates the performance of a machine learning model. It calls a function called evaluation from a module called functions. The function takes multiple arguments, including the test data, x_test, y_test, the model to be evaluated, and some additional parameters like whether to use random samples for evaluation and the number of predictions to make. The function returns the predictions made by the model, pred, the true labels of the test data, y_true, and the predicted labels, y_pred. Additionally, it may also show a graph of the evaluation results if the show_graph parameter is set to true. 4 Bayesian optimization. Python code is defining a function called create_model. The function takes parameters d1, d2, filters, pool, and kernel. Inside the function, it starts by clearing the current keras session. Then, the code converts the input parameters to integers. Next, it retrieves the number of time steps and features from the training data, x_train. It uses these values to create a sequential model in keras. The model consists of a one-dimensional convolutional layer, CONV1D, with the specified number of filters and kernel size, followed by a max pooling layer, max pooling 1D, a flattening layer, flatten, two dense layers with D1 and D2 neurons and ReLU activation, and a final dense layer with one neuron and no activation. The model is then compiled with the atom optimizer, mean squared error, MSE, loss function, and mean squared error metric. It is trained on the training data, x_train and y_train, for 4 epochs, with verbose set to 0, and using multiprocessing for faster training. After training, the model's performance is evaluated using the test data, x_test and y_test, and the model's mean squared error is stored in the score variable. Finally, the function returns the mean squared error, MSE, score. Code is performing Bayesian optimization. Bayesian optimization is a technique used for optimizing hyperparameters of machine learning models. It aims to find the best set of hyperparameters that minimizes or maximizes the objective function. In this code, the bounds dictionary defines the ranges for different hyperparameters filters, D1, D2, kernel, and pool. The code creates a Bayesian optimization object, passing in a function create_model as the objective function, the bounds dictionary, random state, and verbosity level. Then, the maximize function is called to start the optimization process. It takes parameters init_points and n_iter, the number of initial random exploration points and the number of optimization steps to perform. Finally, it outputs the best set of hyperparameters found by the optimization process using the print optimizer.max statement. Python code performs the following actions. 1. Sets the value of n_steps to 21. 2. Scales the TSLA column of the stocks data frame using a scaling function called scale, from the functions module, and assigns the scaled result to a variable called scaled_TSLA. 3. Splits the time series data, the scaled TSLA column, into input sequences, x_train, and corresponding output values, y_train, as well as a separate set of test data, x_test and y_test, using a function called split_sequences, from the functions module. The input sequences and output values are created by shifting the data one step ahead in time, and the splitting is done with a specified ratio of 80% for training data and 20% for test data. For optimization, function in Python is likely an implementation of a Bayesian optimization algorithm. Bayesian optimization is a technique used to optimize functions that are expensive to evaluate, and it is commonly applied in areas such as hyperparameter tuning for machine learning models. The function is likely designed to find the optimal set of input parameters for a given objective function or model by iteratively evaluating different parameter values and updating the search space based on the observed results. Python code builds a convolutional neural network, CNN, model using the keras library. 1. It first assigns the number of time steps and features in the training data to variables. 2. Then, it clears the keras session to ensure a fresh start. 3. A new sequential model is created. 4. A 1D convolutional layer is added to the model with 9 filters, a kernel size of 5, and ReLU activation function. The input shape is set to n_steps, n_features, which defines the shape of the input data. 5. A max pooling layer is added with a pool size of 9. 6. The output from the previous layers is flattened. 7. A dense layer with 250 units and ReLU activation function is added. 8. Another dense layer with 10 units and ReLU activation function is added. 9. Finally, a dense layer with 1 unit is added, which is the output layer without any activation function specified. 10. The model is compiled with the Atom optimizer, mean squared error, MSE, loss function, and MSE as the evaluation metric. Code trains a model using the fit function with the x_train and y_train data for 100 epochs. It also uses the x_test and y_test data as the validation data during training. The training progress and validation loss are plotted using Matplotlib. After training, the model is evaluated using the evaluation function from the functions module. The function takes the x_test, y_test, trained model, and several other parameters. It returns the predictions, pred, true labels, y_true, and predicted labels, y_pred. The evaluation results are displayed as a graph. Bayesian optimization didn't improve accuracy. Results are similar to the previous networks. Finding similar patterns. Hypothesis behind this idea is simple. Can patterns, sequences, found train set be used to predict patterns in test set? Pattern is a sequence of daily stock returns presented as binary values, 0, if return is negative, 1, if return is positive. Example of sequence, 0, 1, 1, 0, 1, 0, 0, 1, 0. The process can be broken down into several steps. 1. Split data into train and test sets. 2. Pick first pattern, with length of 9 days, from test set and collect similar patterns in train set. 3. Compare 10th day of train patterns with 10th day of test pattern, save result. 4. Repeat process for the rest of the patterns in test set. This Python code uses the Matplotlib library to create a line plot of stock returns for the TSLA data. It plots two lines. One for the stock returns from the 2000th index to the 2100th index, and another for the stock returns from the 2001st index to the 2010th index. The first line is plotted with a line width of 1 and is labeled as stock with a blue color. The second line is plotted with a line width of 3 and is labeled as pattern, 9 days, with a pink color. The plot includes a legend, a title, and a label. The plot is then displayed. Pattern matching technique. Code is trying to predict the next value, 0 or 1, in a binary sequence based on patterns found in the training set. Here's a breakdown of what the code does. 1. The code applies a binary function to the return values of the TSLA stock, assigning the result to the variable binary_return. 2. The binary_return array is split into training and testing sets, with the first 2000 values assigned to binary_train and the rest assigned to binary_test. 3. The variables step and check_step are defined. Step represents the length of the pattern, example 001011010, that the code is trying to find, while check_step represents the value that follows this pattern, either 0 or 1. 4. An empty list total_predictions is initialized. 5. The code loops through the binary_test set, selecting a pattern of length step for each iteration. 6. For each pattern, the code searches for matching patterns in the binary_train set. If a matching pattern is found, its index is added to the found_patterns list. 7. The code calculates the prediction based on the values that follow the found patterns in the binary_train set. If predictions are made and the actual value from binary_test matches the prediction, a 1 is added to total_predictions. Otherwise, a 0 is added. 8. After completing the loop, the code calculates the accuracy of the predictions by dividing the sum of total_predictions by its length. 9. Finally, the accuracy is displayed. To the example. Code seems to be visualizing matched patterns in stock returns data. Here's a step-by-step explanation of what the code does. 1. It initializes the variables start and window with values of 1 and 9 respectively. 2. It creates an empty list called A. 3. It selects a sample of data from a binary test. 4. It then loops through a range of length of binary_train minus window. 5. Inside the loop, it checks if the accuracy score of a portion of binary_train data matches the sample with a score of 1.0. 6. If it matches, the index I is appended to the list A. 7. It sets up a figure for plotting with a specific size. 8. It plots the return values of the TSLA stock from 2000 plus start to start plus 2010, labeled as true, with a dashed line, thicker width, and black color. 9. For each index value in A, it plots the return values from TSLA stock in segments of 10, labeling them with the index value. 10. It adds a horizontal line at y equals 0, representing 0 return. 11. It sets the title of the plot. 12. It sets the labels for the x and y axes. 13. It adds a legend to the plot. 14. Finally, it displays the plot. Comparison. Python code creates a line plot using the matplotlib library. It plots the returns of a stock, TSLA, over a certain period. It also plots a pattern of returns for a specific time range, 9 days, within the stock data. It then identifies and plots other patterns within the stock data that match the initial pattern. The code also includes annotations, such as a legend and title, and sets the style and size of the plot. Finally, it displays the plot. Conclusion. Varies depends on the section of the trained data we're working on. Results are inconsistent, but generally approaching baseline model results. Q-learning. 7.1 Using MACD to make decision. Code uses a function called mapped_trading from a module called functions to calculate the profit and the number of trades made based on the MACD indicator for the stock with ticker TSLA during the year 2018. The stocks TSLA.lock 2018:2018 part of the code specifies that we want to analyze the data for the stock TSLA within the time range of 2018 to 2018. The calculated values, profit and trades, are assigned to the variables profit and trades, respectively. Given Python code is used to plot the moving average convergence divergence, MACD, for the stock data of Tesla, with the ticker symbol TSLA for a specific time period in 2018. MACD is a commonly used technical indicator in stock market analysis that helps identify potential buy and sell signals. Code uses a list comprehension to create a new list called companies by iterating over each element in a list called stocks. Then, it initializes an empty list called returns. Next, it iterates over each element in stocks and calls a function called mapped_trading with certain arguments. It passes a subset of the data for each stock from the year 2018, a budget of $5,000, and specifies not to display a graph or return value. The profit and trades variables returned by the mapped_trading function are then used to calculate a return percentage based on the budget and added to the returns list. Code creates a pandas data frame with 2 columns, company and return %. The values for these columns are taken from the variables companies and returns, respectively. The code then sorts the data frame based on the return % column in descending order. You're going to lose money if you use MACD. 7.2 Using Bollinger Bands to make decision. Python code is using a function called bb_trading from a module or file named functions. It is passing in the stock prices for TSLA, presumably representing Tesla, from the year 2018. The function is being called with 2 additional arguments, u and l, which have values of 0.03. The return values from the function call are being assigned to the variables profit and trades. Code calculates the returns of different companies' stocks using a function called bb_trading. The code creates an empty list called returns. It then iterates over each company in the stocks list. For each company, it calls the bb_trading function with specific parameters, including the company's stock data for the year 2018, a budget of $5,000, upper and lower thresholds of 0.03, and options to not show a graph or the return. The BB_trading function returns the profit and number of trades made. The code then calculates the returns as a percentage by dividing the profit by the budget, multiplying by 100, and rounding to 2 decimal places. The calculated return is then appended to the returns list. Python code creates a pandas data frame with 2 columns, company and return, %, using the lists companies and returns as the respective data. It then sorts the data frame by the return, % column in descending order.